The title of this talk is, What is C++? But my expectation is that everyone in this audience already knows what C++ stock is. So we're done. No. I'm not going to answer that question with a list of features or anything like a specification. I'm not even going to describe the syntax. Instead, we're going to see if this works. This is a problem. Wow. All right. Instead, I'm going to address this question from the point of view of what is C++ for? What is C++ trying to accomplish, and how does it accomplish it? Understanding this is important for two reasons. The first is to have a better understanding of how to use C++. And I think that's why most of us are here at this conference, is to learn how to use C++ better. The second reason is that it helps us as we consider how C++ should evolve. Understanding what C++ is trying to accomplish guides us in discussing new language and library features. In this talk, I'm going to explain what C++ is trying to accomplish, how it accomplishes it, and I'll give some examples that illustrate that. Then I'll consider something that I consider one of the most important points of controversy facing C++ today, and how our understanding of the defining aspects of C++ illuminate that controversy. Finally, I'll discuss the implications of this insight for one of the biggest challenges that the C++ community faces today. So, I want to answer the question, what is C++'s superpower? Before I tell you what I think the answer is, I want to explain that C++ has several superpowers, but none of them is unique to C++. Some people might suggest that C++ superpower is flexibility, portability, expressive power, etc. These are all important. But at its root, C++ superpower is uncompromising performance. We try to design C++ to maximize flexibility, portability, expressiveness, safety, etc., but never at the cost of performance. Why do we make that choice? Because this is C++. When faced with a trade-off that gives us better safety, at the cost of performance, we don't accept that trade-off. Why not? Because this is C++. James, you're supposed to be saying this with me.
I'm sorry. Yeah. This is C++.
There you go. All right. Members of the C++ Standards Committee understand that this is what is expected of C++. And the definition of C++ can leave no room for a lower level language. What this means in practice is that although we may add various features to provide us with higher level abstractions, allowing us to reason about code at a higher level, we don't add features that violate the zero overhead rule. Now, this is sometimes misunderstood to think that we don't add features. Added features can have no overhead. It's understandable to think that from the name, but that's not what it actually means. What it means is that if a feature is not used, then we have no overhead. If it is used, then the overhead is no greater than what you would have if you had to implement that by hand. All right. So how does C++ provide this uncompromised performance? Well, there are several ways, but I think the key one is that the user's code is implemented directly with corresponding machines instructions, if they exist. For example, when the user's code calls for adding two integers, this is implemented with a machine instruction to add two integers. Integer division is implemented with an integer division instruction, assuming there is one. But you'd say, surely every language does that. Well, not necessarily. Let's look at some example functions in C++. Okay. So what we have here is three very simple functions, add, multiply, divide. And if we look at how the code is generated, we see they are indeed implemented with a single instruction. But notice, these are not necessarily safe. Right? What is the issue that we're faced with add? Right, we could have integer overflow here. And with multiply, same issue. Now we don't have that issue with divide, but what's the issue we have with divide?
Divide by 0.
Divide by 0, right. Okay, so all of these functions represent a safety concern. So the challenge that we have is that we'd like to be able to have C++ compilers generate code for most, ideally all platforms, and different platforms will handle corner cases in different ways. If all platforms were to behave in the same way for corner cases, we would just define that as the consistent behavior for C++. We wouldn't have this issue. But different platforms are going to have different responses to corner cases. We could pick one. We say, well, this is the defined behavior for maybe it's a popular platform, and we just emulate that behavior on other platforms. But notice the cost of emulating the behavior is going to be slowing down the non-corner case. The common case is going to be slower if we do that. For example, we might have a few options for what the defined behavior for division by 0 would be. We could define the result as returning the maximum value of an int. It's as close to the infinity as we could get. We could throw an exception. We could set a static error flag, something like that. The actual behavior is irrelevant because defining a behavior, any behavior, would mean testing the value of the divisor with every division operation. It doesn't really matter what's done in the division by 0 case. It's the test itself that that means the language isn't able to implement division with a single machine instruction. So with this version, what I've done is I've created a div safe. And the difference is that what it does is in the case of division by 0, it will throw a constant. I mean, this is just about the simplest possible thing you could do to do something reasonable with this. But notice, the output for divide is almost doubled by div safe, and there's a branch in there. And of course, the branch is also going to be a performance killer. And the important thing here is that we deal with that every time we do a divide, whether we're actually dividing by 0 or not. That's the cost that we're going to pay.
But the branching here, in this case, can be removed because you can use cselect, and then it will be fine.
Okay. We'll have to talk about that later. All right. So why is it that we take this choice of using the divide that has the single instruction instead of the divide that would be safer? Why do we do that?
Because this is C++.
Because this is C++.
Do you need a new
Oh.
clicker?
There we go. What's that?
Do you want a new clicker?
It may be the batteries out here. That's possible. So someone might point out that we don't always take this route. So here is std vector looking at the index operator. The index operator provides element access without range checking. But in addition, the standard library provides the @member function, which provides the same service with range checking. Thank you very much. All right, so this is a very rare case where C++ is offering both a safe and an unsafe version. The important thing to note about this case is that in practice, the index operator is the one that's almost always used. If we were to only have one, this would be the one that we would have. Why? Why is it that we would go with the unsafe operation?
Because this is C++.
Because this is C++. All right, one might argue that this is a false feeling of better performance because it's a logic error to attempt to access an out-of-range element. If the library doesn't do that, then we've just pushed this back so the caller has to do the same checking that the library would have had to do. But that's not necessarily the case. It may be that the caller's code accesses a particular element a few times. Maybe it does multiple reads and some writes. And so it only needs to check the bounds once for that particular element, despite the fact that there's many reads and writes. And of course, the would have to do the check on every call. Furthermore, probably the most often way that we access elements in a vector is setting up a loop. And you can set up the loop in such a way that you can guarantee to not have out of bounds. And so in that situation, we would do no bounds checking at all. All right, this leads us to this observation that's often made, that you can build safe on top of fast, but you can't build fast on top of safe. What this means is that given an API that does no domain or other testing, one can build an interface on top of that API that adds any necessary bounds checking, making it safe. But given an API that has domain checking built in, there's no way to remove it for cases where the checking is redundant or otherwise unneeded. And therefore, it's killing performance with no benefit. So with a few exceptions, such as the container member at, the C++ standard library does little or no domain checking, putting the burden of this on the caller. Why is it that the standard library is designed this way?
Because this is C++.
There you go. All right. So the superpower of C++ is undefined behavior. It's the fact that we put constraints on what code we can write to guarantee that the code that we do write can be implemented with uncompromising performance for any target machine architecture. Are there corner cases which would inhibit our ability to implement code with uncompromised performance? Then we put the burden on the programmer to express their ideas in a way that can be implemented with uncompromising performance by declaring those corner cases as undefined behavior. Why do we do this? Because this is C++. All right. So the example I'm about to show you is going to be treated differently by C++ 26. For details, you can read Thomas's paper, but for the purpose of this talk, we'll assume that we're only talking about C++ 23. The details of this specific example will change, but the larger point is still valid. So here's the example. C++ allows us to declare variables of fundamental types without initializing them. Now, the expectation of some naive users, users have used other languages perhaps, is that this code is going to result in the variable a being initialized with the value of 0. This can, will, and does lead to uninitialized variable errors. So experienced users know that this will not 0 initialize, and I guess that most experienced users probably know why. Some users become experienced because they make the wrong assumption in situations like this. If the variable being declared is about to set to the result of some runtime value, maybe from a keyboard, a file, network connection, something like that, then the work done to initialize the variable is wasted. So given the choice between a behavior that leads to fewer bugs and one with uncompromising performance, which is a real trade-off here, which is the one we choose? We choose uncompromising performance. And why do we do that? Because this is C++. So although it isn't the point of this talk, I think that the syntax for this could have been safer without compromising performance. One can imagine a language in which declaring an uninitialized variable means to 0 initialize, as many naive users would assume. But you support a more performant behavior with a syntax maybe like this, right? This is a hypothetical thing. But actually there is a syntax that works today. This is actually legal, and this is exactly what this means, that you don't want to initialize this. Technically, I believe the language actually permits this for user-defined types, but I definitely do not recommend you doing that. So let me point out, since reading from an uninitialized value is undefined behavior, we could at some point define the behavior and make it so that it doesn't break code. We could fix that. So we could, in some future version of the standard, we could say, no, int a now means that this is 0 initialized. Would that break any existing code? Would it break any correct code? No, it wouldn't, because no correct code is depending on how this is interpreted. Would it fix any bugs? Probably a countless number of bugs, right? But we don't take that choice. Right? Why don't we do that? Because it would be some compromise of performance. And we don't do that because this is C++. Okay. All right, so let's drill down on a potential safety issue of an uninitialized object by int in our example, right? What can we legally do with an uninitialized object? Can we read from it? No. We can't read from it. Now, the standard says it's undefined behavior, at least until 26, it's undefined behavior. But notice there has to be a value there. I mean, there's bits, they're either ones or zeros, there must be a value there. But the standard is saying No, this is undefined behavior. So when I teach this in my classes, I'm sometimes asked if the compiler can't track this and catch any undefined uses of uninitialized variables. Yeah, David.
In C++ 26, didn't we standardize it so that int a semicolon would initialize a to 0?
No, it's more nuanced than that. That's why I said I don't want to talk about 26 in the earlier slide. Right, yeah. There is a new interpretation of what this int a without an initial value would be. It's still an error, but we are now defining a behavior to it, which is unspecified what that behavior is, but it's not considered undefined behavior. But I don't want to get into that because it's very interesting, and I think it's an important step forward, but it's not really the point I'm trying to make in this talk. Again, this is just an example of undefined behavior. So where were we? Oh, when I talk about this in class, sometimes people say, can't the compiler track this and tell us about this? So in simple cases, the compiler could warn us about this, and perhaps some do. But notice code analysis tools, static analysis tools are much more likely to be able to do things like that. The thing is, it's not the compiler's job to track the runtime value of something. The compiler's job is to track the static type of something. And that's what the compiler does, and we can rely on it to do that. All right, so consider a definition like this. This function could be compiled in a compilation unit that's different from the one that calls it. And therefore, the code wouldn't be able to detect an illegal use unless you have some kind of whole program analysis tool, maybe the compiler itself, or maybe other tools that do something like that. Now, if you were writing the preconditions for this function, would you indicate that the passed parameter must be initialized? Would you expect to see it if you were looking for the documentation of this function? This is so basic a requirement that obviously the passed parameter has to be initialized. It is so obviously the case that we would rarely spell out that requirement. If you have any value being passed in by reference, it's almost always assumed by the author of the function that that's going to be an initialized object, right? In fact, in my day-to-day use for C++, I rarely think about uninitialized objects, but they are part of the language. In Elements of Programming, Alex Stepanoff and Paul McJones defined the term for a situation where the compiler knows the static type of an object, but its runtime value is not fully formed. They coined the term partially formed. So a partially formed object, the compiler knows the static type, but its runtime value is not fully formed. Now, the very existence of this type, an object like this, is a risk. Inexperienced programmers, naive programmers, careless programmers this is going to lead to bugs. Why do we accept this trade-off?
Because this is C++.
Because this is C++. All right, so the analogy I have in mind is a ski run. Imagine a well-groomed ski slope. If you stay on the defined path, you can ski safely at full speed. But if you wander too close to either edge, danger awaits. At the edge of the ski run, there's rocks, trees, crevasses, maybe even cliffs. If you write C++ code that stays within the bounds of defined behavior, the compiler can generate safe code of uncompromising fast performance. But this can only be accomplished because we only support, that is, we only define the behavior for the most common cases for most operations and place the burden of avoiding corner cases on the programmer. Why do we place this burden on the programmer? Because this is C++. All right. Because it allows us to push support for corner cases, the undefined cases, onto the programmer. So the compiler can generate code that ignores those corner cases. This yields that code of uncompromised performance. So I want to briefly address an undefined behavior issue that can be a surprise to naive users. This issue arises from the fact that compiler writers don't think about undefined behavior the way we might naively expect. So a user that understands that corner cases are undefined behavior and further understands why the language calls them out as undefined might reason that if they are writing code for a particular target environment, and if they understand how that target environment handles a specific corner case, They can safely rely on getting the expected behavior from their code, even if it's technically undefined behavior. For example, suppose a programmer reasons that they know what the target processor does for signed integer overflow, and they're happy with that behavior. They can ignore the fact that it's undefined behavior because the compiler will generate code that does what they want, even if it's not guaranteed. But this reasoning assumes that compiler writer is just going to ignore what might be undefined behavior. And why would they not? The compiler has no burden to generate any code in that case, so they can just ignore those cases. But the reasoning is faulty because this is not how compiler writers think about undefined behavior. It's true that compiler writers could think about undefined behavior that way, and if they did, that would result in compliant compilers. But the compiler writers are after optimum compliant code, and it turns out that they can generate code that is both conforming and faster if instead of ignoring undefined behavior, they make the assumption that undefined behavior can never happen. Now, why is that compliant? Undefined behavior does in fact happen if you have buggy code. So how can they just ignore that? Well, anytime undefined behavior does happen, the compiler writer is effectively off the hook. It doesn't matter what they generate. So they simply assume that it never happens. So let's take a look on the division where we're throwing an exception. So in this case, we're calculating the division. If it turns out that b is 0, then we throw this 0 div, right? So is that exception ever going to be thrown?
No.
Well, if b is 0, then we have undefined behavior. Therefore, anything can happen. So in theory, that exception can be thrown, but it's not going to be. And why is that? Well, the reason is that, again, the compiler writer understands, or the compiler, I guess, at that point, understands that since if b is 0, we have undefined behavior here, we make the assumption then that b cannot be 0, and therefore we do not put the test here to see if b is 0, and we do not put the throw. That code just does not happen. And that's the kind of optimization that compiler writers can do by not just ignoring undefined behavior, because they can do that too, but instead what they can do is they can say, no, undefined behavior doesn't happen, and we don't have to generate any code based on that. So I've been making sorry, kind of went ahead of myself there. I've been making the point that in C++ we live with safety trade-off that puts a burden on programmers. This might lead us to think that C++ is unsafe. In fact, many people make that claim. But this claim fails to understand how applications are developed. It rests on the belief, trivially true, that compilers produce the code that we run. But the deeper truth is applications are produced not just by the C++ compiler, but by the C++ ecosystem. Compilers and the language definition are an important part of creating applications. But so are tooling, testing, documentation, the presence of high-quality libraries, training resources, language culture, and most important of all, programmers. The C++ ecosystem has always been hyper-aware of memory safety issues, and this is an important part of our language culture and is reflected in the work of the Standards Committee, as each release of the language finds new ways for us to be memory safe without compromising performance. CpplusPlus is providing support for new and powerful tools focused not only on memory safety, but other issues of code reliability and performance. Believing that safety is the sole responsibility of the compiler is to misunderstand the application building process and is likely to result in misguided attempts to build in safety at the cost of performance. This is self-defeating in part because performance is itself a component of safety. Applications that are more responsive to changes in the real world are safer than applications with slow response times. Further, a logic error in a memory-safe language is just as fatal as a logic error in an unsafe language. The belief that the use of memory-safe language precludes the creation of buggy applications is a false sense of security. It can get people killed. Imagine an all too likely scenario of a manager that mandates a trendy new memory-safe language that is so new that it doesn't have a ready pool of experienced developers, a well-developed culture, or training resources, who then skimps on tooling to detect bugs with static analysis, or on training so that the development team doesn't use or understand valuable techniques like programming by contract. The likely result will be expensive, buggy software with poor performance. Experience has shown that C++ applications developed by well-trained engineers with access to state-of-the-art tools and techniques will have better performance and be as safe or safer than applications developed in languages with a less robust ecosystem. The industry investment in C++ means that not only will these applications have performance advantage, but likely also a development cost advantage. Mandating that safety be built into the language definition is no guarantee of a safer final application, but it is a guarantee of reduced performance. C++ has been and remains a valuable development tool due to its robust ecosystem and its high performance standard. All right. With the introduction of modern C++, usually C++11 is usually considered modern C++, we introduced move semantics and a syntax for R-value references. This is a major complication to the definition of C++. As someone who makes my living teaching modern C++, I can assure you that understanding move semantics and R-value references is a major challenge for both novice and experienced C++ programmers. Including move semantics in C++ represents a major cognitive load for the payoff of fewer unnecessary copies and perfect forwarding. It may be the single most difficult to grasp feature of modern C++. Why did we add this language complication? Because this is C++, and we do what we need to do to achieve uncompromised performance. So let's look at a specific example of move semantics in action. In the constructor here, we are move initializing one of our data members, and by move initializing, we may be saving what could be a very expensive copy. All right, so what do we know about the list move constructor? Is it a constant time operation? Is it inexpensive? Is it non-throwing? Move operation should be cheap, constant time, and non-throwing. So here is our vector move constructor, and the vector move constructor is no except, but notice the list move constructor is not no except. Why is that? Well, in my opinion, the committee made a mistake and compromised our uncompromised performance. So let's step back and do a review first of move semantics. So I want to describe a set of problems. I want to exclude a set of problems that might arise in legacy code or with irregular types. So let's stipulate for what the discussion I'm about to say, we're not working with any legacy types which don't have move operations or any types that have data members that aren't movable because they're const or references or arrays. So if you have modify access to the source for all the types that we create, that we can create for all the types in our library or application, then we can make certain that each data member is one of three categories. It's either a primitive type, an owning pointer, or a compound type made up of primitive types and owning pointers and compound types. So given this, we can make these rules. For primitive types, we just copy. For owning pointers, we do a copy, but then we zero the source. And if it's a compound type, we create and use move operations that recursively follow these rules. Everybody understand what we're doing here? Simple move operations. Right? Is that all we need to do to make moves? Anything else we need to do? Well, it's not quite all. We need to make sure that our destructor has to be work on a move from object. That's not usually hard, but we need to make certain there's no assumption made by the destructor that wouldn't be valid if the object's moved from. So is that all we need to do?
You also have to be able to assign to it.
Also have to be able to assign to it. So assignment must be safe to unsigned objects. Why do we need to support assignment? Why do we have to support assignment? Isn't destruction enough? Well, it turns out this is a very important use case. We have many algorithms that rely on moving the value from an element so that a new value can be put in that location. And so the ability to assign to an object that's been moved from is very important for sorting, inserting, removing, and uniquing on random access containers. So these two use cases, destruction and assignment, were identified in the very first proposal for move semantics, which described leaving move from objects in a state that is unspecified but valid. In this case, valid meant valid for destruction and assigning to. No other operations were identified as needing to be supported. Valid in this context didn't mean that the object maintained all invariants. So let's note in passing that these are the two exact same operations that are supported for uninitialized private types. In other words, move from objects are what Alex and Paul McJones identify as partially formed objects. Their static types are understood by the compiler, but their runtime values are not fully formed. Now we return to vector and list in the standard library, and what I argue is the standard committee's mistake. The standard says that objects of types defined in the standard library, when moved from, are in an unspecified but valid state, but that here they define valid as supporting any operation that has no precondition. In other words, these are what Alex and Paul would call fully formed objects. So let's look at the implications of this difference for vector. The standard doesn't specify exactly how vector is implemented, but it is an allocated array. And we can determine that there are three required data members, right? A pointer to the allocation, a size for tracking the number of current elements, a capacity for tracking the current allocation size. Note that the size and capacity can be implemented as either integers or pointers. And what I'm saying here is true regardless of your implementation strategy. So let's take a look at a particular static state of a vector, perhaps of integers. So we're pointing at some address where there is the allocated array. The buffer that is allocated is big enough to hold 16 integers, but we only have 10 integers in the vector at the current time. Everybody understand that? All right, now let's do a move from and take a look at, following the rules that we specified earlier, what would we get? What would we get? Well, we're going to simply copy all these. These are primitive types. This is a pointer, an owning pointer. So the only difference is that we're going to have the exact same values, except that the allocation was zeroed out, right? Okay. This is as fast as we could possibly implement, to just make a copy of these things and zero out that. This is a uncompromised move situation. But notice, this doesn't actually work for the standard, because the standard says that if you move from a vector, you can turn right around and call size on that vector, and if the answer is not 0, then you can also call front, which gives us a reference to the first item in the buffer. So by making the decision that the standard made, the committee has specified that the extra work has to be done. Work that isn't normally going to be true. Oops, sorry. So my point is just that even in this very simple case of moving from vector, there is some performance compromise required due to this decision by the standards committee. But vector is not the only case to consider. We noticed that for list, the committee doesn't require that the list move constructor be no except. Now, why not? Well, it turns out that one of the major library implementations chose to use sentinels for their node-based containers. So Wikipedia tells us that Sentinel node is a specifically designated node used with linked lists and trees as a traversal path terminator. This type of node does not hold or reference any data managed by the data structure. So I'm not taking a position here on Sentinel nodes as an implementation strategy. Like all interesting engineering decisions, there are trade-offs. One of the trade-offs is that we need to allocate these nodes when the container is constructed. Since we only need one Sentinel for each container object, we allocate them that one container once on construction. We free them on destruction, and we shouldn't have to worry about them in any other situation. But let's consider the move constructor. If the move from object is now being considered partially formed, and all you're going to do for it is either destroy it or assign a new value to it, then this is sufficient. But if we're saying that the move from object must be fully functional, then it must have a sentinel. And since we're move constructing another object, we have to allocate a new sentinel. And that, of course, means that it's not cheap. We're doing an allocation. And there's the possibility of an exception being thrown. So it's not cheap and it's not no except. Now, that's why the Standards Committee has said that it's not no except. It doesn't mean that some platforms it won't be no except, but it's not a guarantee by the standard that a list construction is no except. So you might ask yourself why the implementers chose to use sentinels given the implications for these operations, for move operations. Well, it turns out that there are trade-offs, and the implementer wanted to take advantage of some of the benefits you get by having sentinels, and at the time this decision was made, move operations were not yet proposed. Your next question might be why the implementation can be changed to not use sentinels. The answer, of course, is this would be an ABI breaking change, and that's a non-trivial ask. Right? So this is the situation we're at. The Standards Committee just fell back and said, okay, it's not going to be no except. And I think that this is a trade-off that comes from the fact that the Standards Committee has said moved from objects have to be fully formed, and it is a performance cost for that. So my real objection to the real reason I say the committee has made this mistake is not because of the performance cost. The performance cost in the case of vector, in fact, most standard library objects, probably not that great. In some situations where you have Sentinel, it's a bigger issue. But that's not my real complaint. My real complaint is this. I think that the Standards Committee is actually encouraging people to make logic errors. If you are querying the state of a moved object, that's a logic error. If you need to know the state of an object, you should not be moving from it first. Right? There's no valid reason to move from something and say, oh, by the way, what's your state? No. If you're planning to move from it, the use cases are assign a new value to it or destroy it. There's no reason for anything else. And by saying to users, by the way, you can move from a vector and then find out what its size is. You're just encouraging people to do something that is a logic error. All right. So in my class, when I talk about move semantics, I point out to students that if and when they move from an object, it's their responsibility to track the object and do nothing with it except assign to it or destroy it. You can feel the anxiety go up in the room. People who hadn't thought about having to have this responsibility are now recognizing that when you use move, you're buying into that kind of burden. But then I explain to them, it's not that difficult for one simple reason. You only move from an object that you intend to either assign a new value to or destroy. It's not like you're going to have to keep its lifetime or some extended lifetime. No, you're moving from it because you know, oh, I'm going to put a new value here, or I'm about to destroy it. That's the only reason you move from it. It's the only valid use case. Now, you might be wondering, well, maybe there's a use case I'm missing. Perhaps there's some legitimate use case. So this was pointed out to me by a friend of mine who's a standard library implementer and a member of the Standards Committee. Now, some of you are thinking the way I talk about the Standards Committee that I probably don't have any friends there. And some of you are thinking that the way I talk incessantly about C++, I may not have any friends at all. But that's not true. I have this friend, and I was telling him that, that these are the only two use cases. Now, I don't have his permission to use his name, so we're just going to call him Inigo Montiel. I told Inigo that there's no other use case for move from objects other than destroying them or assigning them. But he said, no use case we've discovered yet. So, to be fair, that's true. But it's been almost a decade and a half that we've had move semantics. And we've created hundreds of algorithms that utilize move semantics. It seems unlikely that we're going to discover a new use case now. But Inigo gave me an example. He says, suppose I have code that populates a vector with a bunch of pushbacks, and then it moves from the vector. And then it loops again with pushbacks and moving. He said, if the vector remains in a fully functional state after moving, then I don't need to assign a default constructed vector to it before calling pushbacks in the next loop. So I have a couple of answers to Inigo. The first is that his code is making an unwarranted assumption that moving from a vector leaves it empty. Now, he's a standard library implementer, so he knows that's going to be the case, but the standard doesn't guarantee that. But more importantly, this is still calling for compromised performance. The savings that you get in the rare case where not default assigning some before calling pushback is more than offset by the additional cost of restoring full functionality on each move. So why did the committee make this decision? Well, I think it's easy to see why library implementers want this rule. We have a name for invariants that don't always hold. What is the name for invariants that don't always hold? They are called not invariant. Somewhere in here is the right spot. Okay. Library implementers are uncomfortable with the idea that their objects can be in a state where their invariants don't hold. It's cleaner for them to just always maintain their object invariants, even after moves. So I understand this feeling, and I certainly don't want to weaken invariants. But notice that invariants already don't always hold. Imagine you have an object in the stack, and you call its destructor. Do the invariants still hold? Of course not. The lifetime has ended. The object has ceased to exist. But I think that's the correct model for understanding moved from objects. Their lifetime is suspended, right? So the invariants don't hold. That they may be destroyed, in which case now the object is at its lifetime end, or they may be assigned to, in which case the suspended is ended and they're now usable objects again. But this is the mental model that they are suspended. But there's really more motivation than just this. So a clue to the committee's thinking might be found on Herb Sutter's blog, Sutter's Mill. So he, in February 17th of 2020, he posted a blog simply called Move Simply. What he said in there is that moves from objects of well-behaved types need not be treated with any special restrictions. This blog is intended in part to remove the burden that I placed on programmers to track moved from objects and restrict what can be done with them. So I want to point out that Herb is literally my boss. He's the president of the Standard C++ Foundation, which produces CppCon, of which I'm the conference chair. I report to Herb on this. So I have great respect for him and his many contributions to the C++ community. My difference with him on this point is entirely technical. It's not at all personal. So the blog uses the phrase well-defined types because although the committee can make decisions about the standard library, it can't make requirements about how we design our classes. Except that it can, because if the standard puts requirements on the types of objects passed into the standard library, that is effectively making requirements on us. Who's going to create types that can't be used with vector, thread, or sort? So has it done this? Well, kind of. If you read Herb's blog, and absolutely, you should read the comments. In the comments, Sean Perrin provides a link to a couple of notes in the standard. Here's one. So notes are considered non-normative, meaning that they are taken as explanatory comments and are not part of the standard. But the implication here by this particular note, so this particular note is saying that if something is move assignable, then RV, which is the R value that's being moved in this case, must still meet the requirements of the library component that is using it, whether or not T and RV refer to the same object. The operations listed in these requirements must work as specified whether RV has been moved from or not. So this note is saying that for your types, if you're going to pass them into the standard library, and of course, again, that means putting them in a vector, running them on thread, anything you do that uses the standard library, then they're saying that if that object is moved from, it has to be able to do whatever is expected of the object that you passed in when it wasn't moved from. So if you pass in something into an algorithm, the algorithm says this has to be incrementable, then it has to be incrementable whether it's been moved from or not. That's what this note is saying. Now the note, again, does not have the force of law, but this is what the Standards Committee voted on, and there's two similar notes, one for move assignment and the other for move construction. And they are very similar, and this is what they say. Now, Sean, who pointed this out, also provided an example. So here's his example. He's created an array of unique pointers, and the unique pointers are just pointers to int. And now we want to sort that array. So we pass in the begin and end for our array that we've created. And then we create a comparator, right? Now the comparator is not comparing the unique pointers because where they are in memory is not really interesting. It's what the unique pointers are pointing to. So we are dereferencing the unique pointers. Everybody understand what's going on here? Okay. Now the question is, will this comparator work if the comparator is used on one of these objects in its moved from state? Well, we would be dereferencing a moved from unique pointer. Can we do that? No. So this is clearly undefined behavior if this is moved from. So the requirements of sort is that you can only sort things that your comparator works on, and according to the note in the standard, can work on even when moved from. Now notice, and this is Sean's point, that no correct implementation of sort would ever do a comparison on a move from object. In fact, in the entire set of algorithms in the standard library, in any of the algorithms that Sean has created at Adobe, there's never a situation where you're going to apply a comparator to a move from object. Doesn't make any sense. You're going to move stuff a lot. Sort is going to move stuff a lot. So are all the other algorithms we talked about earlier. But we're never going to apply any kind of reasoning to the move from object and the move from state. So in order to be compliant, standards compliant, this code would have to have checks in it to see if the pointers are 0. Notice, they can never be 0. There's no way that these pointers can be 0, not if sort is implemented correctly. But according to the note, this is not standard compliant. Does everybody see the issue? Okay, so this is why Sean brought this up. Sean went further and said, you know, what this note really should say is RV is assignable to and destructible and otherwise unspecified state. Okay. All right, so the blob's approach gives an illusion of safety. It's saying that calling a member function on a move from object isn't going to crash. We have to make it work. But the problem here is that calling a member function on a move from object is a logic error. So crashing immediately isn't the only danger. Bad design is going to result in bugs and buggy applications. So I want to consider the semantics. What is the meaning of these function signatures? Right? So what does the first function signature mean? Well, this signature is saying that this function is taking a non-const L-value reference to its parameter. And so what can it do with that parameter? It's non-const, so what can it do? It can mutate it. But there is a constraint. It must leave the parameter in a valid state. It must not violate the invariance, right? Okay. Now, let's look at the second signature. This is taking a non-const R value reference. Now, this can mean one of two things. If for what Sean and I believe, is that what this is saying is that this function is allowed to modify the widget as long as it leaves it in a valid state, where valid simply means can be assigned to or destructible. But according to the blog post, what this means is essentially that these things have the same meaning. The signatures are the same semantic meaning. In both cases, you can make any changes you want to the widget, but you have to leave it in a completely valid state. All its invariants still have to be there. All right, so the question you have to ask yourself, is that really what you're expecting? All right, so I want to consider one last example. Suppose your OS has some really cool, expensive to create object that's a viewpoint for magic, 3D renderings driven by some kind of AI model. Okay, it's really complicated. But what you do is you call create viewport and a bunch of parameters, and then you get this viewport ID, which is simply an integer, maybe even a pointer, that you pass into the OS in order to do things like all sorts of getters and setters for various properties of our viewport. And then when we're finished with it, we can free it up by passing it into this free function. Right? All right. Now, to me, this is a perfect candidate for wrapping in a C++ object directory. Right? All right. So what we want to do is we want to have a type that has a viewport ID as its member, and that we will initialize that with a call to create viewport. If that fails, returns nil, whatever, we're going to do some RAII, throw an exception. Does everybody follow what's going on there? Some hand waving there. All right, and then on destruction, we're going to see if it's not in a move from state, then we're going to free it. Okay? And then we're going to have a whole bunch of getters and setters that are going to pass in our viewpoint ID to do gets and sets on it. Does everybody see what we're doing there? Okay. So now the question is, how do we implement move operations? Well, you know how I want to implement move operations. What I want to do is simply say, I'm going to make a shallow copy of the viewpoint ID, and then I'm going to zero out the source. Right? Does that make sense? Now notice, if you do this, then your viewpoint ID is 0, and none of those getters and setters are going to work. So it's not following the note. It's not following what the blog post has recommended. So it's not well behaved, according to what the blog post says. So what are our options? Well, one thing we could do is we could do this step here, but then we turn around. Actually, we wouldn't even need to zero that out, because what we're going to do is we're going to call the OS to make a new viewport so that we now have a valid viewport ID. Now all those getters and setters work. What's the issue here? What's the problem with that?
It's now expensive.
It's very expensive. Remember the whole thing, we started out by saying this is an expensive thing to create. The whole reason we want to have move semantics is to avoid having to create this or make a copy of it. Yeah?
Do you know if there's ever been any discussion about trying to make move constructors like implicitly no accept? Like with C++11, destructors were changed to be implicitly no accept. And like my thought is just that it's such a subtle and insidious performance bug, or it can be, that I've just always wondered. Like it's easy to forget to write no accept, and it can have meaningful impact.
Well, again, we have a major library implementation that can't do that.
Right. Well, I mean, you could say no accept false. Like you can do that with a
Sure. I've never heard of that. I mean, you're right. It could be proposed. Okay. Yeah, Bob.
So, John, I noticed in your class declaration that you only have a constructor, and in that constructor, you actually assume that you're constructing the viewport object. That you're actually constructing something as part of the constructor. You don't have a default constructor.
Right.
You don't have a state which represents an empty or null state.
Right.
Now, I would argue that in the case where you have an object that expresses an empty or null state, in other words, the default constructed state, that your argument doesn't apply.
Mm-hmm.
Because move from can in fact be exactly the same as the default constructed state. So you've provided an example here of an object without a default constructed state.
Right. So there's a couple things to say. One is it's not necessarily the case that it's efficient to get to that default state, but probably is. Probably. But the other thing is that creating objects that are in some, not really yet usable state, right? Without the viewport ID, what are you going to do with the viewport? It's not really usable. So you can create this, in a two-stage thing, right? And this is contrary to the whole point of RAII. What RAII means is that resource acquisition is initialization. So if I have the object, I have the resource. Yeah?
Well, I would argue that theoretically that's nice, but it's not always practical, right? I may not always know what I need to construct until some point after the object is constructed, at which I don't always know how I need to configure an object when the object is constructed. I need to construct it in the default state now and configure it later, and that's just the reality of the system I'm working in. I can't change that.
I completely concede that that's the case.
Okay.
But I'm going to ask you to concede that there are other cases where I really want the RAII behavior.
Oh, absolutely.
Right. And in that case, which is what this is an example of, the performance impact of saying you can't be in a partially formed state is, in this case, very expensive. But this is not the only option. We have one other option we can do. Right. So the other, the other thing we can do is go ahead and zero it out, but modify all member functions to fake something when moved from. Right? In other words, we've now made the move from, it's all safe. There's something you can call, and if it has to return a value, it makes up some value and returns it. But notice, those are completely useless calls. And furthermore, they're all a logic error. You've moved from something, and now you're calling a getter or a setter on it? That's a logic error. Right? All right. So, So I would say that neither of these two operations make sense if you're interested in uncompromised performance. Because notice, if you, inside all of these member functions, you're going to have to check for the moved from state. So even if you never move the object, you have compromised performance on all of your getters and setters. In fact, all members of this class are going to be slower because we have effectively weakened the invariant. The invariant should say, if you have a class, you have the resource. If for any reason you don't have the resource, so for example, if you couldn't construct it, then you throw an exception. The object no longer exists. That's what RAI is for. By doing this, we've weakened the invariant, and we've said, okay, if you have a viewport, then you have a viewport resource. Unless you don't, in which case we have weird behavior that's not very useful. All right, so I want to summarize. What is C++? It's uncompromised performance. It's achieved by living with undefined behavior, which means accepting a higher burden for developers and tools. So the committee has decided that for all standard types, moved from means fully formed. That ship has sailed. It isn't going to change. I feel it's a mistake because, for one thing, there's a minor performance hit for essentially all standard types because of this. But there's a major performance hit for some standard types if they're implemented using Sentinels, and perhaps there's others that I don't know anything about that have non-trivial requirements when moved from. But that's not my real gripe about that decision. My real gripe about that decision is that it is encouraging people to make logic errors by saying, oh, move from this and you can still use it as if it wasn't moved from. Is encouraging people to think wrongly about what it means to move from. All right. The direction of the committee seems to be to mandate that moved from objects be fully formed even in user code. And when I say it seems to be their direction, it's because they created this note. The note is merely explanatory, does not hold law, but this is clearly something, it's in the standard, it was voted on by the entire committee. Notes are not just things that people add later. They are voted on as part of the wording. And again, the major hang-up I have here is that it's encouraging logic errors. Programmers should be taught that moved from objects are partially formed and should not be used in any other way. So, I believe that the correct way to think about moved from objects is as partially formed objects. Objects whose lifetimes are suspended. They still exist. They can be revived by assigning to them, but otherwise they are unusable. The only thing other than assigning to them is to let them go out of scope. This is the solution that leads to uncompromised performance. And why is it that we're so focused on uncompromised performance? Because this is C++. All right, so my final and perhaps most important point is that using a language promising memory safety is neither sufficient nor required for building safe applications. It's not sufficient because no language exists, which makes logic errors impossible. It's wrong to think that using any memory-safe language is guaranteed to result in safe applications. Thinking this may lead to a false sense of security. Experience has shown that C++ applications developed by well-trained engineers with access to state-of-the-art tools and techniques have better performance and may be as safe or safer than applications developed in other languages. The C++ ecosystem is a rich culture of resources for building high-quality applications. C++ is high performance. C++ is safe. C++ is evolving to be better in both of these areas and many others. We can have it both ways. We can build safe applications with uncompromised performance. How do we achieve this? Because this is C++. Thank you very much. All right, anybody has any questions? James will answer those now.
I'm sorry, what? I have a question.
Yeah.
Would you be in favor of some hypothetical tool, like say a move sanitizer, that would fault if you ever tried to use a moved from object? Like, is that a kind
Except to assign to it or destroy it. Yes,
Right,
absolutely.
yeah, of course, yeah.
All on board with that.
Yeah.
Yeah, all on board with that. Yeah, David.
I just wanted to kind of comment on your claim that safety somehow has an impact on performance with safe languages. And I just have a couple of things I wanted to say about that. The first one is that if you look at the data and performance comparisons between a safe language built for performance like Rust, I mean, they're neck and neck with C++. The second one is just the simple example that you gave where you had like int I semicolon, and now in C++ we're going to make that auto assign to 0. For C++ 26 we're not talking about that. Right now it's undefined behavior if you like read from that. Whereas with a safe language like Rust, it actually tracks to see if it is set before you use it. So you get the performance without the unsafety. And the second example I want to give is that, in particular with Rust, because of its lifetime rules and analysis, it knows that there's no aliasing when you have functions. So these are like pointers that you pass to a function to make sure they don't overlap each other. And because of that, the compiler is aware of that aliasing not being possible, is able to further optimize that faster than C++. And just the comments that you made about the ecosystem and all that kind of stuff, I think it's important to recognize that for a language like Rust, it's as popular now in terms of like number of developers using it as C++ was, N years ago, like 10 years ago or something like that. I find a lot of value in C++. I think you really hit spot on in terms of like the going with the undefined behavior as like the way it's achieving performance. But I shy away from discounting the safety and performance approach of a new language because I do think that there's actually a lot of value and additional safety guarantees that you get from using something like that versus C++.
Very valid, yeah. I think also that the committee is looking at that and trying to figure out how do we get safety without compromising performance. And I think we're making strides in that area. Yeah.
I think it's a bit disingenuous to say that Rust is neck and neck in performance in C++, arguing grounds of safety, because Rust still has the unsafe notation to say, hey, turn off the safety for this, specifically so it can get the extra performance.
Yeah.
Yeah, I was just going to ask, so the fact that the list move constructor is not no except was a revelation to me. I had no idea about that. Does the standard even specify what happens? Like if list throws or something like that in a move, does it even specify what the state of either object is afterwards? Like it's
Well,
because like do you just lose
so
the list?
if you're constructing an object and you throw, the object doesn't exist.
Mm-hmm. Right, but what I'm saying is that like have you just lost the state of the list? Like because like is either object in a good state at that point?
I would have to think about that a little bit. I suspect it's pretty well defined, but I don't know.
Yeah, because I mean, like, I don't know, my experience with throwing move constructors is that they're just hostile to the language. Like, it's, like, you can't deal with them. It destroys an object, and now you don't know if either object is in a good state.
Well, you know, for history buffs, the reason no except exists is because of types. Classic example is just a pair. Imagine you have a pair, and so it has two components, and you're wanting to move them. And the first one moves, and the second one throws on its move. Well, what's the state? You know, and so that's why no except was invented, to be able to clearly say it's safe to do this because we're going to guarantee that there's no throw.
Yeah.
There's a number of optimizations in the library that happen because you guarantee that it can't throw.
Yeah.
Because trying certain algorithms, if you were to, let's say, copy a number of elements over, and then on one of them they failed, you can't roll it back. There's nothing you can do. So the library will fall back to classic code, meaning it's going to copy everything, unless you guarantee that this move operation is no except, and therefore it will then use that optimization. That's why it's so important, as you were asking earlier about when you have move operations, you really want to declare them as no except, because if you don't do that, you're going to get poorer performance.
Yeah, what I mean, my fear is just that like a throwing move constructor is almost as bad as a throwing destructor. Like not quite as bad, but
Yeah.
almost.
Yeah. Yeah, and as I pointed out, you can almost always write a move operation that is cheap, no throw. There's certain, if you're using a type from classic C++, that type has no move operations, but it does internally allocate or do other things that might throw on construction, you got a problem. There's no way around it, and you have to, your move operation, if this is one of your data members, has to be possibly throwing. But we're getting further and further away from that situation now. And so we're close to a situation where we pretty much just assume that a move has to be cheap, constant time, no except, unless we can't. I'm not hearing any other comments. James didn't heckle me nearly enough. James, did you?
I'm sorry. I was trying to be nice for once.
Oh, I'm sorry, James. You don't happen to have a twin brother, a nice twin, do you? Yeah.
One other thing I was curious about. So like when it comes to like unchecked like bounds accesses and stuff like that, like we were talking about for vector and stuff having .at. So like the only thing that I wondered about on that one, so like I assume that there must be platforms where this is a meaningful optimization, because like my thought has just been, I don't know, like most like modern CPUs these days, like you have a branch predictor. Like it's the only case where it would be mispredicted is when you made a logical error and you're about to corrupt memory anyway. And so like I've just always been a little bit skeptical of that argument in general. Like, is it just that, I don't know, on like, like low power embedded devices or something like that, they don't have as rich pipelines as like big CPUs? Or like, I'm just trying to understand, because it seems to me that most of the time, like you're gonna get good prediction on, not throwing, because if you are like, if you would take the throwing path, it means your application has a logical error in it.
I'm not sure I completely understand what you're saying.
I just mean that like I would expect that the cost of the branch in like a safe, like in a checked bounds access would be correctly predicted very, very like regularly. Like my thought is just that like I've always been skeptical of the argument that that's just a significant performance optimization by not having that branch.
David,
you might maybe have an answer. Yeah.
I can actually respond to this because on the committee for in-place vector, we did a bunch of benchmarks to see checked access versus not checked access, and on all like Intel platforms, you pretty much get the checked for free.
Yeah,
there's no difference.
That's what I was thinking.
On Mac, like the new Mac chip, whatever, we did see a very, very slight performance degradation on there. There was people hypothesizing that if we did it on an embedded chip, it might be worse, but we weren't able to get benchmarks from that.
Okay.
But I think for the vast majority of the cases, you do actually get the check for free to do that.
That was my thought as well. But
did you have a comment?
Yeah, I just want to add, it depends on the CPU. So there are CPUs that their ground prediction will cost more if they will mispredict. So to clean all the pipes will take time. And with the newer CPUs, it's actually becoming worse. Because they are taking more in, then they have to clean more.
Like, I think the idea is that, like, if you mispredict, it's already gonna take
Oh, yeah.
you already have an error.
Yeah.
It doesn't matter
Yeah.
how long it takes. Like, as long as I think the issue is just like it's very application specific, right? Like, it might be okay without those. Your program might be running well because, like, the thing is, it's a finite resource. Branch predictor doesn't have infinite capacity, right? At some point, it's gonna fill up. At that point, if the default branch prediction is wrong, then it's gonna be like there must exist one program where, like, if you enable these checks by default, it's actually gonna start to perform worse. Even though some of them actually are completely inefficient.
Yeah, well, I mean, I would expect, like, the standard library could itself, like, seed the predictor and say, like, you know, like, I don't know, like the unlikely macro or something like that, like, basically say, like, you know, this is the predict against the exception being thrown. But, yeah.
There's more than just the branch predictor though, right? I mean, just having extra assembly is gonna fill up the function.
True.
The instruction cache, right? So.
Yeah, I guess really it's just in my personal experience, I've never seen enough of a performance diff for me to think that the total lack of any sanity checks really makes sense, but, yeah.
Okay, oh, yeah.
Do you think that outside of this place, this room, that the debate over whether or not to continue using C++, like in some of the press releases Dave was talking about, versus moving to other languages, is being oversimplified and is missing the idea that there is great value in the ecosystem, as you say? And if so, how does this community answer that in a way that's understandable to people who are reading headlines?
I really don't know. I mean, one of the things I've thought about is, how would you explain this to someone who's not a programmer? Say, well, there are languages that are safe and languages that aren't safe, but you can still make safe applications in unsafe languages. But if you use this other language, I mean, you can't really explain the subtleties of what's going on. You just got this label that says, well, it's safe because there's certain kind of errors you can't make.
Right, it's safe an overstatement.
Well, David, what do you feel?
I would just say that when deciding what language to use, you have to look at the trade-offs, right? And there are a lot of trade-offs in favor of C++. One of the biggest ones is compatibility with C++ because there's so much code that's been written for it. But it's not just that, it's also like quick ability to change without having to refactor your code and some of these things that are very great for specific domains, like especially like games and stuff like that. And safe versus unsafe, it's really, I think it has to be contextualized, like what are you writing? If you're writing something which is processing credit cards and is getting external input which might be untrusted, then the trade-offs will probably be in favor of like a safe language. But it's not like a either this or that. It is so dependent on a bunch of different factors. And I think that's probably how we need to communicate that.
So I worked for Boeing for 5 years. And I took it to
the door?
What's that?
Did you work on the door?
No, I did not work on the door.
There's your heckle.
But I did, thank you very much, yes. I went back to visit and saw some of the people I'd worked with and stuff. And this was, I don't know what it was, 3-4 years later. And they told me, and I should have mentioned, all the time I was there, Boeing was a completely blue shop. It was all IBM everywhere. And when I went back, they told me, we now have several people from HP on the board of directors. And they said, you know what that means? And I said, yeah, it means that decisions are going to be made at the wrong level. And I think that's part of the problem is that the trade-offs that David's talking about, you know, this may be the optimal language for this application and this might be for this. But the people who are making these decisions sometimes are not the people who are in a position to make those kinds of decisions. Yeah, Bob.
Well, I just wanted to make a comment, plug for the conference, and the people who are interested in exploring and understanding the question of safety can refer to last year's conference where we had 3 keynotes and a 2-hour panel discussion dedicated to the topic of safety and how is it defined and how is it applied in our various respective industries.
Oh, yeah.
Yeah, so I
will play the devil's advocate right now, and I will say most of the things that you showed and said this is C++ will make it really hard for a new programmer that comes to your company to run C++. How do you reply to this?
Because I was immediately showing them all the undefined behavior.
You cannot show everything, right?
Right. And one of the things people have pointed out, we don't have a document that lists all the kinds of undefined behavior we have in C++. It is scary. But generally speaking, when I've encountered something that's undefined behavior, it's never been a surprise. It's like, and sometimes it's the other way. It's like, no, this works. You sure that works? Yeah, trust me, this works. So I don't know what to tell you except that I think that one of the biggest non-technical challenges facing C++ is that engineers are not well trained, right? What I used to tell people is that the bad news is that college professors have stopped teaching C++. The worst news is that sometimes college professors do teach C++, and it's worse than if they didn't. So that's the problem. People coming out of college, getting a job, they don't understand C++. Now, Bob plugged his conference. I'm going to plug myself and say, companies need to hire people to come in and talk to them about how to raise their C++ skills and C++ knowledge. If that works for you, give me a call. But the problem is that there's a lot of people who are using C++ full-time on a day-to-day basis, and the lack of knowledge is scary.
I think you very convincingly argued that C++ puts the responsibility on the programmer to avoid undefined behavior. But as history shows, we're not very good at avoiding these bugs. And if a bug can lead to a security vulnerability that can be exploited, the cost of that is not borne on us or our employers, it's borne on maybe other customers or businesses or governments or individuals. If we individually or our employers were liable for these bugs, do you think we were still using C++?
I think that many companies do look at themselves as liable for what their products do, and work very hard to prevent those kinds of issues. So I don't know that. I mean, C++ isn't going to be dropped overnight. There's a huge investment in C++. It's not going to be dropped overnight, and there may be a race between how long people continue to use C++ and how long it takes for the standards committee and the tooling people to make it so that it's considered a safe language, because there's so many ways of catching these kinds of bugs without affecting performance. I don't know what the future holds there. Don't know what to tell you. Okay, well, I've appreciated your attention and following along. And now if somebody asks you what C++ is, you can tell them. Thank you very much.